Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module HR Diagram Part 1 from the paper Astronomy and Astrophysics. After studying this module, you should be able to recognize a HR diagram. Then next, you will be able to explain the coordinates of an HR diagram. You will be able to appreciate the shape of an HR diagram. Then next, you will be able to understand that in this diagram, stars appear in distinct families. Then you will be able to recount the characteristics of these families. You will be able to recognize that there is a real gap in the horizontal branch of the diagram called as the Hertzsprung gap. Then next, after studying this module, you will be able to explain that during their evolution, stars pass very rapidly through this region and therefore there is a real paucity of stars there. Then next, you will be able to derive the shape of the plot at a given stellar radius. And in the end, you will be able to explain that the stellar radius and mass increases upwards in the HR diagram. Now, before beginning into the details of the module, let us have a brief introduction. In the last few modules, we have discussed the stellar spectra and spectral classification based on stellar spectra. The Harvard system of spectral classification categorized stellar spectra in 7 major classes, from simple spectra containing only a few lines to a spectra containing a huge number of lines and molecular bands. The major classes were named O, B, A, F, G, K and M. Each major class was further subdivided into 10 subclasses running from 0 to 9. Considering the bewildering variety of stellar spectra, classes Q, P and Wolf-Rayet had to be introduced at the top of the classification, and classes R and N were introduced at the bottom of the classification scheme. Some prefixes and suffixes were also suggested to be used with the spectral classes to take account of special features of their spectra. Earlier, it was thought that the difference in spectra was due to the evolving chemical composition of the stars. However, in 1920, Saha showed that the progression of spectra from class O to M could be explained in terms of the decreasing surface temperature of stars. Saha likened the process of ionization of atoms to a chemical process and derived what we now called Saha's ionization formula. This formula gives the fraction of ionized atoms as a function of temperature and pressure in the stellar surface layers. Taking the examples of atoms of hydrogen, helium and calcium, we showed in the last module how the intensities of lines of these atoms vary with temperature in agreement with the spectral classification. In this module, we discuss a type of plot which has become an important diagnostic tool for the astronomers. HR diagram. We have already seen that astronomers are always on the lookout for relations which help them to study the objects of their interest. One such relation is the one between some measure of the luminosity of a star and some measure of its surface temperature. The relation found independently by Hertzsprung and Russell is named after these astronomers and goes by the name of Hertzsprung-Russell diagram, that is HR diagram. HR diagram is one of the most useful tools for the study of stars and their physical properties. Coordinates of an HR diagram. Besides luminosity itself, absolute magnitude is measure of luminosity. The measures of surface temperature are spectral class and color index. Therefore, the coordinates of an HR diagram are those shown in the figure below. Note that the surface temperature increases towards the left while the color index increases towards the right. Similarly, the absolute magnitude being anti-correlated with luminosity increases downwards. So the diagram given here is for the coordinates of an HR. Diagram are luminosity or absolute magnitude along the y-axis and surface temperature, color or spectral class along the x-axis. The surface temperature decreases towards the right. Similarly, absolute magnitude decreases upwards. Figure given here shows the coordinates of an HR diagram. HR diagram of the nearest stars, even this small sample shows the emerging of families of stars. The Sun, shown by a yellow circle, is the main sequence star. We can see a yellow circle in the figure given below. The topic is schematic of HR diagram. In the given figure, we can notice that the temperature and luminosity scales are not linear. Various stellar families are identified. The density on the main sequence is indicative of the actual stellar numbers of stars on it. The red vertical line shows that a star of a given spectral class can belong to any family of stars. The figure here shows the schematic of the HR diagram, and the density on the main sequence is indicative of the actual stellar numbers of stars on it. Separation of stars in neat groups is immediately noticed. Stellar families. So students, let us first study about the stellar families. In the HR diagrams, the group of stars running from top left to the bottom right is the most populous group. This group is called the main sequence. On the main sequence, the luminosity steadily decreases as we grow from early to the late spectral classes. The lower region of the main sequence is more crowded than the upper region. The stars at the lower end are red in color because of the low surface temperature and are very small in size. These stars are therefore called red dwarf stars. These are the most abundant stars in the galaxy. Then another group of stars is situated below the main sequence, occupying the left bottom corner. The stars in this group have luminosities like those of the red dwarfs, but their surface temperatures are much higher. These stars are known as white dwarf stars. In abundance, there are next only to the red dwarfs. That their name is descriptive of their size is clear from the fact that the white dwarfs are about 10 magnitudes fainter than the main sequence stars of the same surface temperature, and so must have very small surface area and radius. HR diagram with 22,000 stars plotted from Hipparcos catalogue and 1,000 from the Gliese catalogue of nearby stars. The diagram has been prepared by Richard Powell. Also shown in the diagram are the luminosity classes. The luminosity classes we will study in the next module in detail. We can see well in the figure the HR diagram with 22,000 stars plotted from the Hipparcos catalogue and 1,000 from the Gliese catalogue of nearby stars. Please notice the use of the color index, that is BV, surface temperature and the spectral class along the x-axis. In the HR diagrams, the group of stars running from the top left to the bottom right is the most populous group. This group is called the main sequence. On the main sequence, the luminosity steadily decreases as we go from the early to the late spectral classes. The lower region of the main sequence is more crowded than the upper region. The stars at the lower end are red in color because of the low surface temperature and are very small in size. These stars are therefore called red dwarf stars. These are the most abundant stars in the galaxy. Another group of stars is situated below the main sequence, occupying the left bottom corner. The stars in this group have luminosities like those of the red dwarfs, but their surface temperature are much higher. These stars are known as white dwarf stars. In abundance, they are next only to the red dwarfs. That their name is descriptive of their size is clear from the fact that the white dwarfs are about 10 magnitudes fainter than the main sequence stars of the same surface temperature, and so they must have very small surface area and radius. Next in abundance are the stars called giant stars lying above the main sequence. These stars are much brighter than their surface temperatures would suggest, indicating that they are large in size. That is why they are called giant stars. The giant branch is almost horizontal, the luminosity of giants changing little with their surface temperature. These stars belong mostly to spectral classes F, G, K and M. Brighter than the giant stars by about 5 magnitudes are the supergiant stars having radii of about 100 R. In this group too, luminosity does not change much with spectral class. These supergiant stars are the least abundant stars. Between giants and the main sequence, there is a group of stars called the subgiant stars. These belong mostly to the latter spectral classes. Finally, between the main sequence and the white dwarf stars are the sub-dwarf stars. The given figure or the plot shows a plot of apparent magnitude of stars against their color or spectral class, which looks like a scatter plot. There is no correlation of the type found in the HR diagram, and there is no separation of stars into families. Such a plot is not of much use. That means the given plot shows the lack of correlation between the apparent magnitude and the spectral class. The diagram given here shows an HR diagram with the instability strip and its components are highlighted. There is a real paucity of the supergiant stars of spectral classes A, F, and G. This defines a real gap in the supergiant branch. This gap is called the Hertzsprung gap. The reason for the presence of this gap is that during their evolution, stars stay at its location for a very short time. Following comments can be called for about the HR diagram shown in the above figure. The first comment then we can make is that the stars are found all over the diagram. The groups simply define the locations where the stars tend to congregate. Secondly, there is a real paucity of supergiant stars of spectral classes A, F, and G. This defines a real gap in the supergiant branch called the Hertzsprung gap, which we can see in the figure. The reason for the presence of this gap is that during their evolution, stars stay at this location for a very short time. Then we can note that the HR diagrams shown above feature the stars found in the spiral arms of our galaxy and other galaxies. These stars are so-called population 1 stars. These are young stars. The stars found in the globular clusters and in the central bulge of the galaxy and other galaxies are generally old stars. These are known as population 2 star. The HR diagram of the population 2 stars is quite different from that of the population 1 stars. We can see in the given figure, as we mentioned above, that the stars found in the spiral arms of our galaxies as well as in the other galaxies are young stars. The figure given here is the Messier 80 globular cluster in the constellation Scorpius, located about 10,000 light years from the Sun and contains hundreds of thousands of stars. Their youth is due to the fact that there is a continuous star-forming activity in the gas and dust found in the spiral arms. These stars are called population 1 stars. Stars found in the globular clusters and the bulge of our galaxy are old stars and are called as population 2 stars. In globular clusters, there is little gas or dust left for the formation of new stars, so no new stars are being formed. The figure shows the typical HR diagram of a globular cluster. The HR diagram of stars in the globular clusters is quite different from that for young stars. There is a main sequence, then there is turn-off to the giant branch. There is a horizontal branch with the Hertzsprung gap. As we shall see, This diagram mimics the evolutionary path of a star on the HR diagram. Importance of HR diagram. The importance of HR diagram to astronomers can hardly be overstated. HR diagram is an important tool for them since all physical properties of a star can be read from its location on the diagram. The diagram has been called the horoscope of stars because astrologers claim that they can read the events of the entire life of a person from birth to death from her horoscope. Luminosity and temperature of stars are, of course, the coordinates of the diagram and can obviously be read. As we shall just see, the radius of a star, the mass of a star, its spectral type, its color, the processes of energy production in its core, its age and stage of its evolution can all be inferred from the location of the star on the HR diagram. Whenever a new object is discovered, its location on the HR diagram is of prime importance because it gives clue to all of its physical properties. The given graph here shows the HR diagram of globular cluster M3. We can see in the diagram that the foot of the diagram is the main sequence. Then there is a turn off from the main sequence. The horizontal branch with the Hertzsprung gap is also clearly seen. Most of the stars belong to spectral classes F, G and K. The luminosity of a star is given by the Stephen-Boltzmann law, which is given as L equals to 4 pi r square into sigma into T की power 4. For the sun, we have the form of formula as solar luminosity equals to 4 pi radius of the sun square sigma into T to the power 4. We express luminosity, radius and surface temperature of a star in solar units. Then its luminosity can be written as L equals to R to the power 2 into T to the power 4. In terms of logarithmic, we can write this equation as log L equals to 2 log R plus 4 log T. So for a fixed R, this equation represents a straight line in the log T log L plane. The graph given here also shows the plot between the log T and log L, and for the fixed R's there is a straight line. So for the different R's, that is R1 and R2, we got the two straight lines where R1 is greater than R2. The given graph here shows the HR diagram showing many details such as lines of constant stellar radius are seen. We also see that as we go up in the HR diagram, the radius of the star increases. Since the mass of the star depends on its radius, mass of the star too increases upwards. Notice the figures on the main sequence. The colors in the diagram are indicative of the colors of the stars. Examples of stars belonging to the various groups on the HR diagram are also given. So students, let us summarize what we have learnt in this module. First of all, we learned about the HR diagram. What is a HR diagram? HR diagram is a plot of some measure of the luminosity of stars against some measure of their surface temperature. Then we learnt that the stars arrange themselves into neat families on the HR diagram. Then we saw that there is no such correlation between the apparent magnitude and the surface temperature. Next, we learnt about the major families, which are supergiant stars, giant stars, main sequence stars, and white dwarf stars. The red dwarf stars on the lower reaches of the main sequence are the most abundant stars in the galaxy. Then we saw next in abundance are the white dwarf stars, which lie about 10 magnitudes below the main sequence. These stars are very small in size. Then we saw that next in abundance are the stars called giant stars, which are really huge in size, lying above the main sequence. Then we saw very bright supergiant stars are rather rare. They lie about 5 magnitudes above the giant stars. The radii of supergiant stars may be as large as 100. We saw that there is a real paucity of supergiant stars of spectral classes A, F and G. This defines a real gap in the supergiant branch called the Hertzsprung gap. The HR diagram of old stars, called as the population 2 stars, found in the globular clusters is different from the HR diagram of the young stars, which are also called as population 1 stars. In the HR diagram, the radius and mass of the stars increase as we go up. Thank you.